Okay, continuing on with Unit 14, some advanced applications of trigonometry. This is 14.2, and the I can statement, our objective for today, is I can represent complex numbers in rectangular and what's called polar form. So we're going to write the word polar right here. We'll get to why it's called that way in just a few minutes, but a quick warm-up here. It says find the modulus of the following numbers. So we've got this number right here, clearly a complex number, so this is what we did in the last section. So we're going to take the real part, take the real part, -6, and we're going to square that, and take the imaginary part, 2, we're going to square that. So this is a 36 and a 4. So let's see, that's the square root of 40, and 40 would be a 2 times a 2 times a 2 times a 5. So this would be 8 times 5, and we've got a pair of 2's here, so we can take that out, and then a 2 and a 5 stuck underneath, so that's going to be a 2 radical 10 for the modulus there. And then this one, this is just a plain old -8. So let's find the modulus of that. Let's use the formula that we were talking about in the last section. I'm just going to put plus 0i here. And we're going to use the formula. So the formula is we're going to take the real part and we're going to square that. We're going to take the imaginary part. We're going to square that. So we end up with, this is a 64 plus a 0. Whoops, plus a 0. Make that look like a 0. So this is the square root of 64. So the answer on this is 8. Now, remember, modulus is the same as absolute value, especially if we're looking at something like this. So even though this was just a real number, had no imaginary part, if you think about where that is, that's over here on the real axis. So how far is that from the origin? How far is that from 0? Well, it would be 8 units away from 0. So it's kind of comforting that this formula works no matter what type of number we start off with, whether it's a complex number with both a real and imaginary part, or just a real part. So keep that in mind. You might see some interesting problems similar to that a little bit later. So when we use rectangular form of a complex number, it can get kind of cumbersome when we're doing operations. So when we're adding, subtracting, multiplying, dividing, all those sorts of things, especially when we're finding powers or roots of complex numbers. Now, we're not going to be doing a whole lot of that in this course, but we would like to get a sense of how we can use complex numbers and use these type of operations. But one interesting thing is if we write a complex number in what we call polar form, these operations they have the potential to be a little bit easier, especially finding powers and roots of complex numbers. So when we write a complex number in polar form, what we do is we basically recognize that each complex number, so take this complex number right here, can be located using a couple of different things. We can use the distance from the origin, okay? Distance from the origin, which is right here, which we can also call the pole, and an angle measured from standard position. So I'm going to write the word standard right here. And just a quick reminder, what we're doing here is we're measuring, so this is going to be the radius, this is going to be how far away from the pole it is, and then we open up this angle right here, that's going to be theta. So I've got that represented here in both cases. So let's talk about how we can actually put a number, a complex number, in polar form. So the polar form of a complex number, and another word that you might hear people use is sometimes they'll call it, instead of polar form, they'll call it trig form. I tend to call it trig form more often than I call it polar form, so just be aware of that. So if we've got a number in standard form, rectangular form like this, then if we write it in polar form or trig form, it's represented like this. So z, again, that complex number, is going to be r cosine of theta plus I sine of theta, where r is the square root of a squared plus b squared, so the real part squared plus the imaginary part squared. So this is basically the modulus. So we'll write modulus right here. Okay, and theta is an angle in standard position whose terminal side contains the point a comma b. So we'll come over here and take a look at this. So here's our point a plus bi on the complex plane. Here's our real axis and our imaginary axis. And what we want to know is we want to know two things. We want to know how far away from the origin is it, and we want to know what angle would this have to be. So how much would we have to open this angle up in order to have it line up with this point AB on the plane there. So let me show you another quick example. Let's say I have the point AB and it's over here. Okay, so I'll do an A and a B over here. In order to write that in trig form, I would need to know two things. I would need to know the modulus. I'd need to know how far it is from here to here. So I do an R right there. And then I need to know how much would I have to open up that angle. So that angle would have to go all the way over here. So you notice that the red one, so I'll do a theta right here. So for the red one, this would be an acute angle the way this is represented right here. And for the blue one, this would be an obtuse angle. It would be greater than 90 degrees if we wanted to think of it that way. So just kind of a visual there. So let's talk about the process that we would use for this. So if we're going to convert from rectangular to polar form, then we do this, kind of like we were showing up above. First thing we're going to do is we're going to find the modulus. That's our formula right there, and we're going to think of that as the radius. And then we're going to use tangent inverse, and you'll see why that's important, but we're going to do the tangent inverse of b over a, and that's going to find theta for us. Now, I'm going to put a little asterisk right here, another one. Would you go ahead and put one there? We want to use caution when we're using inverse trig functions, and you'll see why in just a little bit. It's really important that we're careful with that. So let's go ahead and follow this process right here to convert from rectangular to polar form on the example number 1. So we're just going to follow the instructions, do exactly what it says. So we're going to find the modulus. So we're pretty good at finding the modulus at this point. This is going to be 3 squared plus 3 squared. We've done that before. This is going to be the square root of 18 because this would be 9 plus 9. So we get 3 radical 2. Okay, so we've got the modulus. We've got that taken care of. And then it says use the tangent inverse. So I'm going to go ahead and pull up the calculator. So we want to do tangent inverse of b over a. So in this case, that's going to be, this is b and this is a. So this is going to be 3 over 3. So let's see what the calculator gives us on this. Quick reminder, make sure you're in degree mode. Later on, when you're taking calculus and stuff like that, it's always going to be in radian mode, but go ahead and check the mode. Make sure you're in degree mode. I'm going to hit second quit, clear this off, and I'm going to type in tangent inverse of 3 divided by 3. And yes, you're welcome to simplify that to be a 1. And you end up with 45 degrees. So we just have to write this in polar form. Now here's what polar form looks like again. Okay, so we could slide it up here and say, oh, this is what it is. It's got to look like this right here. Whoops, let me just do this part. Okay, that's polar form. So I'm going to slide this down here, and we're going to write down, okay, we've got to have r, that's the modulus, so I'm going to write down 3 radical 2, and then in parentheses I'm going to write the cosine of 45 degrees plus, and then it's I in front, sine 45 degrees. Okay, so we've done exactly what they asked. We wrote this in polar form, so we've got polar form right here. And this is rectangular form, just to be clear on this. So this was in rectangular form, we converted to polar form, and we're all set to go. So let's visualize what's going on here, because this is the number 3 plus 3i. So again, here's the real part, here's the imaginary. So I'm going to go 1, 2, 3, 1, 2, 3. So we're going to put a point right here. This is 3. This is also 3. And you might recognize this, and we can say, hey, if what we were interested in was the radius, if these two are the same legs on a right triangle, this has got to be a 45, 45, 90. So that's got to be a 45 degree angle measured from standard position. So we've got 45 degrees right here. And we can go from a leg to a hypotenuse just by multiplying by radical 2. So this is going to be 3 radical 2. So we could have figured this out visually and then figured out, oh, the angle that we have to open this up to turn to get to this point on the plane is 45 degrees, and we would have to be 3 radical 2 units away from the pole. So there's polar form right there. Okay, so that's how we change that. So you want to be familiar with this idea, and pictures like this, they can be really helpful. But one quick thing we want to take a look at is, it should be really clear by now by why we call polar form by trig form also. It's also called trig form. So we call polar form and we call it trig form. Those are both the same thing, okay? So again, I tend to call this trig form. Other people call it polar form. Again, it's probably how you were taught and how you learned and stuff like that. I learned it as trig form, so that's kind of what I stick with. And then you may also see r parentheses cosine theta plus I sine theta. You might also see it abbreviated this way. So it's r and then cis theta. And sometimes we'll call this cis notation. So r cis theta, because this is pretty long to write out. Now, for the time being, I do want you to write this out. But if you ever see r cis theta or something written like that, that's what we're talking about. So if you see an I in something, a lot of times it deals with imaginary numbers. So we're going to go ahead and take a look at what's on the other side. Okay, so let's go ahead and take a look at this example right here. You'll notice the instructions say the same thing. We're going to convert to polar form. It does say be careful with inverse trig functions. That's going to come up on each one of these, so we're going to want to make sure that we're very careful with this. So I'm going to go ahead and do this without the sketch first and see if we can just follow the process and see what happens. So on this, the first thing we're going to do is we're going to figure out what the modulus is. We're going to figure out the radius. So this is going to be negative 2 radical 3, and we're going to square that, plus 2, and we're going to square that. So this is going to be, let's see, if I square a negative 2, I get a 4. If I square square root of 3, I get 3. And then this is plus 4, so this is the square root of, let's see, 12 plus 4, so this is going to be the square root of 16, so we end up with 4. So here's our radius, and then theta is going to be the tangent inverse of, let's see what our calculator gives us here. So I need to do the tangent inverse of 2 over negative 2 radical 3. So I'm going to pull up the calculator. I'm going to make this a little bit smaller here, and we're going to type into the calculator tangent inverse, and I'll just write it like this, 2 divided by, and I'm going to put this in parentheses, so I'm dividing by the entire thing. If you don't put that in parentheses, then you're going to get that wrong. So this is going to be 2 and square root 3, and I need to make that negative. So I got to come back here. I'll close the parentheses, so we've closed them completely, and I'm going to put a negative right there. So I'm going to insert a negative. Okay, so I think I'm in good shape there. I've got that typed in right. Okay, so it says negative 30, which strikes me as a little bit odd because we don't see negative angles very often. So I'm going to do something else. I'm going to type in tangent inverse, and this might give some people a little bit of comfort and make it a little bit easier. I'm going to do this with fractions. So I'm going to hit alpha y equals, and I'm going to put a 2 on the top and a negative 2 square root of 3 on the bottom. Hop outside there, close the parentheses, make sure that looks good. The nice thing about these calculators with this pretty print, as they call it, is you can look at it and you can make it look exactly the same. It's not quite as hard as, you know, gosh, did I put the parentheses around the right thing and stuff like that. So I'm going to hit enter, and I end up with negative 30. So then I've got an issue here. So remember we said you've got to be careful with inverse trig functions. So here's the deal, and this is why a sketch is going to be so important. So let's sketch where this is. This is at negative 2 radical 3 for the real part and 2 for the imaginary part. So this part would be 2. So the point is right here, and we found the radius. We found that this modulus was 4, and then you'll notice that we have to measure this angle from standard position. The problem here is the calculator doesn't give us the angle from standard position. Inverse trig functions are pretty complicated, and we'll talk a little bit more about that in a few minutes. But what it's doing is it's giving us the reference angle. So the reference angle, let's ignore the negative there. The reference angle is 30 degrees. So that angle right there is 30 degrees. You might recognize that this is a short leg and this is a long leg. Remember we said that if the relationship between the two legs on a right triangle are multiplying or dividing by radical 3, you've got to have a 30, 60, 90. This is the smaller of the two, so this is the smaller of the two angles. This isn't a 60-degree angle. That's going to be 30. And then, of course, to go from the short leg to the hypotenuse, you multiply by 2. So this is 30 degrees, which means this angle is actually measured from standard position. It's 150 degrees. So what we have here is we have 4 for the radius, and then we're going to have cosine of 150 degrees plus I sine 150 degrees. And that is our answer. That we have taken that number up here and we have converted it from rectangular form and we've written it in trig form or in polar form. Okay, so I'm going to make this big again so we can go through and do the next one. This one, let's go ahead and draw a picture of what this looks like. This is going to be negative 2 and then negative 4, so it's going to be about like this. And I'm kind of drawing it roughly to scale, so negative 2 and negative 4. So we've got a right triangle that looks like this. And at this point, you really don't even have to think about the formula for the modulus, which is a squared plus b squared underneath that square root. You can just say, oh, I'm just going to take the leg and I'm going to square it. The horizontal leg happens to be the real component. The vertical leg, that happens to be negative 4, and I'm going to square that. So I get 4 plus 16, so I end up with radical 20, and we've done this one before. This is going to be 2 radical 5. Now, we do prefer to keep these in exact form, so let's go ahead and keep that. You'll notice that this is not something that we recognize. Having a leg be double the other leg, there's no special relationship there, so we are going to have to use inverse trig in order to find this. So let's go ahead and do tangent inverse of, and we're going to do negative 4 over negative 2, which is the same as doing the tangent inverse of 2, but let me go ahead and pull up the calculator. So we'll do tangent inverse of negative 4 divided by negative 2, we'll hit the answer, and we get this right here. I'm just going to, for the heck of it, I'm just going to recall. Actually, I'm just going to hit tangent inverse because that's going to be faster. -4 divided by -2 is 2. And I hit enter, I get 63.43. Yeah, 43. Okay, but the problem is this angle measured from standard position is not 63.43, but this angle right here, the reference angle is, so 63.43. So how do we figure out what the entire angle is? If this is 63.43, how do we figure out what the whole angle is? Well, from this is 90 and this is 180, so it's going to be 180 plus that measurement right there. So we'll grab the calculator, we'll just hit plus 180, and we end up with 243.43. So if we write this in polar form, this is going to be 2 radical 5, and then we write cosine of 243.43 degrees plus I sine 243.43 degrees. And you'll notice it takes quite a bit of space to write these. So hopefully hopefully you're writing better than I am. But then we've got this one right here, and this one's kind of interesting. So let's just blindly go through and let's just follow the process. So we're going to figure out what r is. So r is, let's see, that's going to be 0 squared because the real part is 0. This is -7 squared because the imaginary part's -7. So this is 0 plus 49. Square root of 49 is 7. So we've got the first part of this. So I'm going to go ahead and start writing down 7, and then it's parentheses cosine some sort of theta plus I sine same theta. So let's figure out what those are. I'm going to put a box around this, and let's see if we can have the calculator figure this out for us. Let's see, this would be 0 plus, 0 minus 7. 0 minus 7. 0 minus 7i. So that means theta is going to be tangent inverse of, let's see, it's -7 over 0. So let's see, tangent inverse of -7 divided by 0, and it's going to give us an error. So we've got to think about this. Where is this and why is there a problem? So let's take a look here. A -7i, that would be straight down here, 7 units. So we're good with the radius being 7 units. We got the modulus there, so we're in good shape there. But this angle right here, our calculator won't give that to us. And if you remember from the unit circle and when we studied that, you'll remember that the tangent of 90 degrees is undefined. Okay, doesn't exist. There's sometimes where you'll see a trig table or something like that that'll say it's infinity. Okay, there's no number to represent what that is. It's enormous. Okay, so we don't have to get into all that, but our calculator's not going to give us an answer, but we do know for a fact that, hey, if it's down here, let's just march off the angle ourselves. Each one of these is 90 degrees, so this would be at 270 degrees. So this is cosine 270, sine, I sine 270. So I do want to take note of this right here. So I'm going to shrink this down just a tiny bit so we can kind of see what's going on and then also see what's down at the bottom here. So because inverse trig functions are more complicated than regular trig functions, and here's why. They have restricted domains and ranges. And kind of talking about that and studying that, not part of this course. Just realize that when you're using inverse trig functions, you've got to be a little bit more careful. So the point here is that when we use tangent inverse of b over a, and remember what b is going to be this opposite side over here, and a is going to be the adjacent side over here. That's why we're using tangent. If we do that to find theta, and I've got theta in air quotes here, it's only going to give us the size of the reference angle. Okay, so that's why when we found this one and it said -30 degrees, we kind of ignored the 30 because what the calculator was doing is it was finding the tangent of an angle over here, and that could be represented as -30 degrees. Okay, so it'll give us the size of the reference angle, and this is where it's important to think about our sketches and our mental pictures that we've drawn here. So which quadrant is the complex number in, so we can use that theta that we found to measure the angle from standard position. So I'm going to write standard right here. Okay, so standard position. And again, those mental pictures are going to come in really handy. So I'm going to go back full screen on this. Whoops, full screen on that and full screen here. And we're going to take a look at the last couple of problems. So on these last few, and I'm hoping this is relatively easy, because just like we can change a complex number from rectangular to polar form, we can also do the opposite. So in other words, we can change from polar form to rectangular form, okay, that a plus bi form. And to do this, we use the angle and the modulus to find the horizontal part. So remember, the horizontal part is going to be the real part. And we can find the vertical part, or that's going to be the imaginary component. So I'm just going to write imaginary right here. And let's figure out what's going on in these examples. So it says convert to rectangular form. So these are already in trig form or polar form, and we want to convert this. So a sketch could be helpful, but it's not going to be required. So here's what I'd like to do. I'd like to just take this 5 radical 2, and I'd like to figure out what the cosine of 135 degrees is. So if you'll remember from your unit circle, 135 degrees is over here. It's a 45-degree reference angle. So this is negative radical 2 over 2, and this is radical 2 over 2. So the cosine is negative radical 2 over 2 plus I, and then the sine is radical 2 over 2. And then I'm just going to distribute. So if I distribute, here's what I get. I get 5 over 2, and I get radical 2 times radical 2. That would make a 2, but then the 2's are going to cancel, so I end up with a 5. Okay? If I multiply here, I have a 5, radical 2, and I have an I and a radical 2 over 2. Radical 2 and radical 2 make a 2, and those are going to cancel with this 2, so I get plus 5i. Now, if you look really carefully, this is really easy to do. I made a tiny mistake here. What I didn't do is I didn't carry that negative with this, and if I lose that negative, then I'm in big trouble. So what I get here is I get negative 5 plus, negative 5 plus 5i. So if I were to look at this and draw a picture of what this looks like, this is 135 degrees, so kind of like I drew over here. Whoops, let me make it look like that. And then this is 5 radical 2. Okay, 135 degrees right, 35 degrees right here. Well, that means there's 45 degrees right here, so that means to find the leg of a 45, 45, 90, I'm going to divide by radical 2. So that's going to make this 5. That's going to make this 5 also, because they're both the same. And then we need to keep in mind what quadrant we're in. So this is negative 5 for the real part, so we can match those up. And this is positive 5 for the imaginary part. We can match those up, and there's our answer. Now, just to be on the safe side, I'm going to grab the calculator. I'll shrink this down just a little bit. And I just want to show you that this will actually work out exactly. So I'm going to do 5 square root 2. And then I'm going to multiply it by the cosine of 135. So the cosine, cosine of 135. And I'm in degree mode, so I'm hoping this works. Look at that, negative 5, so we got that. So basically what I just did is I just distributed 5 radical 2 times the cosine of 135. Okay, and then I'm going to distribute right here, and the cool part here is I can just recall this, come back here, change the trig function that we're working with. So we're going to type in the sine right there, and it tells us that that's 5. So the imaginary part, the real part, that's negative 5. Okay, that's the cosine. And then the imaginary part, that's positive 5. So it does work either way you want to do it there. We're going to take a look at this one and see if we can figure out what's going on here. I am going to draw a picture of this one first, and then we'll go from there. So what we're looking at here is 210 degrees. So 210 would be, let's see, 180 is right here. So 210 is going to be 30 degrees past this. So we've got a 30-degree reference angle. And this is the radius, remember. This is the modulus. So this is radical 3. So let's see. If this is a 30-degree angle, this is the short leg. So to go from the hypotenuse to the short leg, we're going to divide by 2. So this is going to be radical 3 over 2. And then I'm going to multiply by radical 3 to go to the long leg. So if I have radical 3 over 2 times radical 3, that's going to be 3 over 2. Now, again, keep in mind where we are. So this needs to be negative radical 3, so we go back. So our real part's going to be negative radical 3, and we go down here. So in rectangular form, this is going to be negative 3 over 2 plus I radical 3 over 2. And you might notice that I'm putting the I in front here. It's a little more typical to put the I in front than it is to put it behind, especially when we have radicals. Right here, because we didn't have any issues with that, that was just a plain old number, an integer, we put the I at the end. But what we don't want to have happen is somebody confuse this and think, oh, the i's underneath. So that's why when we've got a radical, we typically put the I in front. If you were to put it in the back, it wouldn't be the end of the world. So before I pull up the calculator, you might notice I made a little mistake here. We want to go ahead and make this negative because we've got negative for the real part and negative for imaginary part. So there's our answer right there. And now I just want to pull up the calculator and I want to check and see, hey, can I make this work out if I type in the radius, the modulus times the cosine of 210 and so forth. So I'm going to pull this up and I'm going to type in the square root of 3 and then the cosine of 210. And the calculator is going to give me negative 1.5. So great, that matches up with this. I can even change it to a fraction. That works out great. So if I did write negative 1.5, I guess that wouldn't be the end of the world. The other one is a little bit more interesting. So if I were to recall this and change this to sine, oops, let me hop in here, change that to sine, I'm going to get this. I'm going to get negative 0.866. And because this is an irrational number, the calculator is not going to be able to change this into a nice format for us. So if you did by chance write 0.86, I guess it would be 0.87 if we rounded to the nearest hundredth. If you did write it like that, that's not the end of the world, but the nice thing is if we know what the angle is, especially those reference angles and the common angles, this is going to be much better. So that's probably the best way to write that. Okay, let's take a look at this one. This one is different. This one is, you'll notice, written in cis notation. So what this means is 8 cosine 320 plus I sine 320. And take a second and think about the angle 320 for just a minute. 320 is over here, all the way over there just a little bit, and we've got a radius, a modulus of 8. We're looking for a positive real part and we're looking for a negative imaginary part. But the other thing is 320 is not a common angle, one that we would recognize. So what I'm going to do is I'm going to shrink this down and let's have the calculator find this for us. So we're going to type in 8 cosine 320, hit enter. So we get 6.13, so positive value right there, 6.13. And then let's see what we get when we do the sine of that. So this is going to be sine of 320, and we get negative, so minus 5.14 and an I on there. Now, this should kind of make sense because you'll notice that this is a little bit bigger. I'm going to make this full size here and zoom in just a tad. Okay. I'm always kind of a fan of taking a good look at this and seeing, do the numbers kind of make sense in the context of where we've used them? So on this, if you take a look, 320 degrees, now 315 is a 45, 45, 90 for a reference angle. 320 is just a little bit long, little bit bigger angle. So this is going to be, the adjacent side is going to be a little bit bigger, and this is going to be the small side right here. So we do get a real part that's a tiny bit bigger than the imaginary part right there. So hopefully you're feeling okay about this. Basically, this entire thing is about, can I represent complex numbers in rectangular and polar form, and can I go back and forth? All right, good luck with the assignment.